Welcome to another edition of Coonrod's Corner. Today's topic, enhancing millimeter wave antenna performance using Radix 3D Printable Dielectric. Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation. I am a technical marketing manager. Today I'm going to be talking to you about Radix, which is our 3D printable RF material. Now you can use that material in a lot of different ways, and today I'm just going to show you a few examples of more structures that we have printed with this material and tested. Now there is a previous Coonrod's Corner video for the Radix material, and it is an introduction to the material as well as showing you some of the capabilities. And I am going to touch on that lightly just to give you a brief overview of the Radix material and capabilities, and then after that I'll show you a little more information on some RF structures that we've been experimenting with. The graphic shown here is a quick overview of the Radix material. It is a RF material, very good RF properties, and it is 3D printable, and you can use DLP as the process for 3D printing, which is a process that's very fast and can be used in higher volume manufacturing. We have worked with a partner of ours, Fortify, and they make these machines. They are a manufacturer of DLP printing systems, and they have allowed us to really understand the formulation better and also how to go about printing this material to where we get very consistent results. And below here in the pictures you can see our formulation of the material that Roger's done is shown on the left. It is a liquid format, or that's how it's sold, and then the DLP printer from Fortify, they will print it in whatever design is given to them, and then to the right is some pictures that have been done of Radix in different formats. Shown in this picture is using Radix to use Grin technology. Grin stands for gradient index, and it's basically a spatially variant dielectric constant. Now to the far right, we're showing how you can do that with a Lundberg lens. And what we're seeing here is the outer shell of this lens has a decay very closely matched to air, which is 1. And you can see as you go deeper into the material, the dielectric constant increases, and that's due to the matrix becoming more dense until you finally get to the core, which is just about the dielectric constant of the Radix material itself. Now in doing that, you can design a lot of different features that will respond very well with the Grin technology. In this case, we're showing in the larger pictures here a Lundberg lens, and we have tested this lens at I believe about 28 to 34 gigahertz, and we got very good results on that, and that can be seen in our previous Coonrod's Corner video. There are many different structures that you can use Radix for to build different RF structures, and the list is actually very long. I've got a lot of things on my list I'm really interested in, but I decided to do something rather simple, and that is just use Radix to print a 3D structure that is a radome, and also a radome with some lens effect. So that's the latest thing I've been working on, and I'll show you some results, and I'm basically sharing my learning curve here. And it is our first attempt, so they're not perfect, but actually they came out pretty good. So let's go ahead and take a look at some of these the experiments we've been working on. Shown here is our test vehicle, and it's a simple microstrip series-fed patch antenna. It is designed to operate at 77 gigahertz, and I am showing the radiation pattern here that we have tested this structure in our anechoic chamber, and it performs quite well. Shown here are several different experiments that I drew up. These are just quick drawings to show the concept. But what I did was basically look at radomes of different structures. The top one is just a simple rectangular radome. The next one down is a radome that has an arc of a set thickness. And in theory, between that and the rectangular radome on top, you should see a difference in the angle itself and what kind of angle error you would get. So with the rectangular radome, depending on what angle the signal's coming in from or being transmitted out of, you could get a little difference in the signal length with the rectangular radome. With the radome with the arc cover, that actually is going to have the same signal length going through the radome. So you're going to have very little difference in the angle of the signal as it's coming in or out of the radome. And then the radome, the third one down, that's the same concept as the second one, except we're using Grin on the inside and outer layers, and that helps with the transition from the dielectric constant of air to the dielectric constant of the solid Radix material that's in the middle. And that can help with several things. It actually can have a lens effect, but it can also help doing matching between air and the radome itself. And then finally, the bottom one is one I'm more interested in, and that's actually a radome with a lens effect. And in this case, it's a pretty simple lens effect to collimate the radiation pattern. So essentially, before and after the radome being applied to the circuit, you would have a radiation pattern that is rather broad, and then once you put this lens radome on the circuit, it will be more collimated and more direct. And also you can see that I have different dielectric constants here. The dielectric constant of 2.8, that is the current dielectric constant with Radix, our current product. Works very well. The other dielectric constant I'm showing here of 4.6, that's experimental, and that's not open on the market right now, but we are experimenting with it. So I decided to go ahead and take a look at differences in dielectric constant with these radomes and lenses. Shown in this picture is one of our radome experiments, and that's actually in the upper left, and it is applied on top of our microstrip series fed patch antenna that I showed on a previous graphic, and it works pretty good actually. So what you can see in the bottom left picture is our measurements and the simulation for the radome being applied to our test vehicle. And you can see the measured versus simulation, and they're pretty closely matched. You do see some differences there, but that's really just from us not optimizing it yet. This is our first attempt, and I'm sure we can optimize it to match it a little better. All things considered, being first attempt, that's actually pretty good. And then off to the right, we're looking at radiation patterns of this being tested in our millimeter wave anechoic chamber, azimuth on top, elevation on the bottom. Again, you can see that the patterns of the simulation, which is green, and the patterns of the actual measured device, red, they match pretty closely. Now, I do see a little bit of difference in the azimuth, and that's something I'm pretty sure we can smooth out. It's not anything dramatic, but that's all part of the learning experience, and those shoulders on right and left of the center of the azimuth, I think I know where that's from, but again, we're going to have to do some experimenting, which is pretty common when you work with a RF structure for the first time. Here are the results of another radome experiment, and this one actually has a lens effect to it as well. So this is supposed to collimate or cause a little more directed radiation pattern, and it did make a little bit of difference. And we do see between the simulation and the measured results a pretty good match. Again, being our first attempt, I feel pretty good about it, but we do have room to optimize. So the top left picture is showing the radome / lens. Bottom left is the S1 parameters comparing measured to the simulation. As you see, they match pretty closely. We do have a little room in there for optimization. And then off to the right are the azimuth and elevation charts from testing the structure in our millimeter wave anechoic chamber. Again, this is centered at roughly 77 gigahertz. And we do see some differences in the azimuth with the red, which is measured, compared to the green, which is the simulation. Again, those shoulders on the left and right of the center of the azimuth, pretty sure I know what that's from, and it's just a matter of experimenting to optimize it. But again, it does show the concept, and it does show it's matched pretty good, actually. So that's our latest for the radome experiments. In summary, the Radix material is a very good material for RF applications, very low loss, controlled dielectric constant, it's isotropic. There's a lot of benefits to this material. And I've showed some examples of how you can use the material with different RF structures, in this case, radomes. However, you can use Grin technology to create different types of lens, different radomes, several different RF structures. So this is just an example of things that can be done. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.